Example 6. Solve log of 50x plus 25 minus log of x equals 2. In order to rewrite in exponential form, we need a single logarithmic expression on the left side of the equation. Using the difference property of logs, we can rewrite the left side. Log of 50x plus 25 divided by x equals 2. Rewriting in exponential form reduces this to an algebraic equation. 50x plus 25 divided by x equals 10 squared equals 100. 50x plus 25 equals 100x, 25 equals 50x, x equals 25 divided by 50 equals half. Checking this answer in the original equation, we can verify there are no domain issues and this answer is correct. Try it now. Solve log of x squared minus 4 equals 1 plus log of x plus 2. Example 7. Solve natural log of x plus 2 plus natural log of x plus 1 equals natural log of 4x plus 14. Natural log of x plus 2 plus natural log of x plus 1 equals natural log of 4x plus 14. Use the sum of logs property on the right. Natural log of x plus 2 multiplied by x plus 1 equals natural log of 4x plus 14. Expand. Natural log of x squared plus 3x plus 2 equals natural log of 4x plus 14. We have a log on both sides of the equations this time. Rewriting in exponential form would be tricky, so instead we can exponentiate both sides. E raised to the natural log of x squared plus 3x plus 2 power equals e raised to the natural log of 4x plus 14 power. Use the inverse property of logs. X squared plus 3x plus 2 equals 4x plus 14. Move terms to one side. X squared minus x minus 12 equals 0. Factor x minus 4 multiplied by x plus 3 equals 0. X equals 4 or x equals negative 3. Checking our answers, notice that evaluating the original equation at x equals negative 3 will result in us evaluating the natural log of negative 1, which is undefined. That answer is outside the domain of the original equation, so it is an extraneous solution and we discard it. There is one solution, x equals 4. More complex exponential equations can often be solved in more than one way. In the following example, we will solve the same problem in two ways. One using logarithm properties and the other using exponential properties. Example 8a. In 2008, the population of Kenya was approximately 38.8 million and was growing by 2.64% each year, while the population of Sudan was approximately 41.83 million and growing by 2.24% each year. If these trends continue, when will the population of Kenya match that of Sudan? We start by writing an equation for each population in terms of t, the number of years after 2008. Kenya of t equals 38.8 multiplied by 1 plus 0.02464 raised to the t power. Sudan of t equals 41.3 multiplied by 1.0.0224 raised to the t power. To find when the populations will be equal, we set the equations equal 38.8 multiplied by 1.0264 raised to the t power equals 41.3 multiplied by 1.0224 raised to the t power. For our first approach, we take the log of both sides of the equation. Log of 38.8 multiplied by 1.0264 of t power equals log of 41.3 multiplied by 1.0224 raised to the t power. Utilizing the sum property of logs, we can rewrite each side. Log of 38.8 plus log of 1.0264 raised to the t power equals log of 41.3 plus log of 1.0224 of t power. Then utilizing the exponent property, we can pull the variables out of the exponent. Log of 38.8 plus t log of 1.0264 equals log of 41.3 plus t log of 1.0224. Moving all the terms involving t to one side of the equation and rest of the terms to the other side, t log of 1.0264 minus t log of 1.0224 equals log of 41.3 minus log of 38.8. Factoring out the t on the left, t of log of 1.0264 minus log of 1.0224 equals the log of 41.3 minus the log of 38.8. Dividing to solve for t equals log of 41.3 minus log of 38.8 divided by log of 1.0264 minus log of 1.0224, which is approximately 15.991 years until the populations will be equal. Example 8b. Solve the problem by rewriting before taking the log. Starting at the equation, 38.8 multiplied by 1.0264 raised to the t power equals 41.3 multiplied by 1.0224 raised to the t power. Divide to move the exponential terms to one side of the equation and the constants to the other side. 1.0264 raised to the t power divided by 1.0224 raised to the t power equals 41.3 divided by 38.8. Using exponent rules to group on the left, 1.0264 divided by 1.0224 raised to the t power equals 41.3 divided by 38.8. Taking the log of both sides, the log of 1.0264 divided by 1.0224 raised to the t power equals the log of 41.3 divided by 38.8. Utilizing the exponent property on the left, t log of 1.0264 divided by 1.0224 equals log of 41.3 divided by 38.8. Dividing gives t equals the log of 41.3 divided by 38.8 divided by log of 1.0264 divided by 1.0224, which is approximately 15.991 years. While the answer does not immediately appear identical to that produced using the previous method, note that by using the difference property of logs, the answer could be rewritten t equals log of 41.3 divided by 38.8 divided by log of 1.0264 divided by 1.0224 equals the log of 41.3 minus the log of 38.8 divided by the log of 1.0264 minus the log of 1.0224. While both methods work equally well, it often requires fewer steps to utilize algebra before taking logs, rather than relying solely on log properties. Try it now. Tank A contains 10 liters of water and 35% of the water evaporates each week. Tank B contains 30 liters of water and 50% of the water evaporates each week. And how many weeks will the tanks contain the same amount of water?